This is chapter 10, part 4 of Introduction to POMP Models, and we're going to look at spline smoothing and see how it has a linear Gaussian POMP representation. And this is going to maybe give us some insights into both spline smoothing and linear Gaussian POMP models. So spline smoothing is a standard method to smooth scatter plots and time plots. It's smooth spline in R and HP filter that we saw in chapter 9 are both spline smoothers. So a smoothing spline for equally spaced time series Y star is the sequence x1 to n minimizing a penalized sum of squares defined as follows in equation SS1. So there's a sum of squares of differences from the data yn star minus xn squared. And then there's a sum of squared second differences. And then there's a smoothing parameter lambda that says how heavily we're going to weight that sum of squared second differences. The spline's defined for all times, but we're particularly concerned with its values at the data points at times t1 to n. And here, just as a reminder, delta n is the first difference operator, 1 minus bxn. So in the intuition for smoothing splines, lambda penalizes x1 to n to prevent the spline from interpolating the data. And the boundary case is if lambda is 0, the spline goes through each data point, in which case x1 to n will interpolate the data because it has no penalty for being as wiggly as it wants to be in order to make the penalty, the yn minus xn squared term 0. At the other end, if lambda is infinity, then the spline will have to be chosen to have 0 penalty term, in which case you'll need the second difference of the spline to be 0. And the solution to that is to have the spline as a straight line. Xn is alpha plus beta n, in which case delta squared alpha plus beta n is 0. And so the spline problem is just the least squares straight line. Now we're going to introduce a linear Gaussian model. It won't be immediately obvious that this is the same thing, but that's what we have to show. And our linear Gaussian model is given in equations SS2 and SS3, where the SS2 looks a little bit like a second difference operator, right? If we shift the 2xn minus 1 minus xn minus 2 to the left, we'd have the second difference operator of xn equals epsilon n. And SS3 is Gaussian measurement error model. And the reason I put the xn minus 1, xn minus 2 on the right in SS2 is to make it look like a natural way to write an AR2 model. So we want to show that, that this is the same as SS1. And we're also going to claim that this SS2 and SS3 has an LG-POMP representation. It's not quite immediately an LG-POMP, but it's a little exercise to build something that is exactly an LG-POMP. So let's do that. If we set xn tilde to be xn and its lag, then xn tilde, which is xn minus 1, we can write this as 2 minus 1, 1, 0, xn minus 1, xn minus 2, plus the noise term. And this in turn becomes 2 minus 1, 1, 0. This thing here we recognize as x minus 1 tilde. And then I'm going to call this thing epsilon n tilde, where this is just exactly what it has to be to make everything match. And this is a kind of common strategy for coercing things into the form of a POMP model. The strategy we followed was to put all necessary lags into the latent state. Okay, so SS2, SS3 is an LG-POMP, and now we want to check that it also matches the penalized spline definition. And there's a nice little bit of algebra to do this. It's not too critical for this course, but let's go through it. And so the SS2, SS3 implies a joint density of X and Y, which we can write as the density of X times the density of Y given X. And if we take logs, then the log joint density becomes the sum of the logs. And now if we write this in the particular form, taking advantage that for a Gaussian density, the log likelihood has a negative sum of squares term, and it also has some other term that just depends on the variance of the Gaussian distribution, and a constant term from the point of view of the x's. So in equation 22, we can just write the sum of two squared terms times their variances. This is the Gaussian log likelihood plus the constant c. A little wrinkle to do with the initial values. Really, c could depend on the initial terms x0 and x minus 1, which formally show up in the likelihood. We suppose these can be ignored, for example, by modeling them with an improper uniform density. So we're going to leave them out of the calculation. And so if we compare equation 22 with SS1, we see that maximizing this joint density is the same problem as finding the smoothing spline by minimizing the penalized sum of squares. And now we're going to argue that this maximization is closely related to the filtering problem, because the key here is that for a Gaussian density, the mode, which is the maximum of the density, is the same as the expected value. And so let's run through the reasoning. We found that the minimum penalized sum of squares is the maximum of the joint likelihood. The change from minimum to maximum is because of the negative sign that shows up in the log likelihood. Now, when we have the joint likelihood, we can divide through by the marginal likelihood of y 1 to n, because it doesn't depend on x, and we're taking a maximum over x. And that is exactly the conditional density of xn given y1 to n. That's the smoothing density. And the argmax is the mode, but that's the same as the expected value. And so we found the smoothing expectation that comes out of that. Now, because a conditional normal distribution is characterized by its conditional mean and variance, what we've done by finding this conditional mean and variance of xn given y1 to n equals y1 to n star, we've basically done the smoothing calculation. And so we conclude that the smoothing problem for the LG-POMP model is the same as the spline smoothing problem. And this gives you a connection both ways. If you have experience with non-parametric regression, smoothing splines, then you can think of POMPs as a related case. If you have experience with POMP models, it might help you understand spline smoothers that are commonly used in many applications. One example of this, when you're doing spline smoothing, there's this smoothing parameter lambda. It's sometimes hard to know how to choose it, but once you think of it as a parameter in a POMP model, and you can calculate the likelihood of different values of lambda, then you have an objective way to do that. To me, this also raises the question, why should you penalize by the sum of the squared second differences when you smooth? And here's one way to phrase that in question 10.5. We found that the smoothing spline corresponds to a particular choice of LG-POMP model. Why choose that choice rather than some equivalent penalty from some other LG-POMP model? And well, here's my take on that, which I think is, it's really a historical accident. The spline penalty happens to match the physics of a thin metal plate bent to match data. Now, this was actually done this was a technical drawing technique where the plate was called historically a spline. Now, this is not a statistical justification. It's a historical accident. And I think what's going on here we're constrained by software that just happens to use this penalty. So I'm not saying that the smoothing spline penalty is always unreasonable. It seems to be quite reasonable in a lot of situations, but presumably there are other occasions when some different LG-POMP model would lead to a superior penalty. So we've worked through some examples of LG-POMP models. Now it's time to develop the equations for the special case of a linear Gaussian POMP model. So the Kalman filter is the name given to the prediction, filtering, and smoothing formulas in the special case of a linear Gaussian POMP. And because linear Gaussian models have Gaussian conditional distributions, we know that we're going to end up with filtering and smoothing and prediction distributions that are Gaussian, that are determined by their mean and variance. And so it's got to come down to linear algebra calculations. And that's exactly what the R function ARIMA does. It uses this Kalman filter to estimate the likelihood of an ARMA, ARIMA, SARMA, SARIMA model, and so on. To go through this calculation, which, by the way, this calculation is not too critical for the course, but it's nice to see how it's done. And so let's go through it. We're going to start by reviewing the multivariate normal distribution. And so what does it mean to say X is multivariate normal? Well, if it's multivariate normal with mean mu X and variance sigma X and it has dimension dx, that means we can write X equals HZ plus mu X, where Z is a vector of dx independent, identically distributed normal 0, 1 random variables. H is a dx by dx matrix square root of sigma x, meaning HH transpose is sigma x. And such a matrix square root exists for any covariance matrix, though it won't in general be unique. And so that defines the multivariate normal distribution. There's an associated density as long as sigma x is invertible, which has this fairly well-known form where here, this is the determinant. So if the determinant's not 0, then this density is well defined. And so now we've defined the multivariate normal distribution. We also want to be able to talk about joint multivariate normals. So x and y are joint multivariate normal if the combined vector z, which is the vector of x put together with y, is multivariate normal. And then we tend to write mu z as mu x, mu y, and sigma z as the matrix, with the top left matrix being sigma x, the bottom right matrix being sigma y, and covariance matrices off the diagonal. A basic property of joint multivariate normal random variables is this formula for the conditional mean and variance of x given y equals little y. So these are given as equations kf1, kf2. I expect you've seen them before. I'm not going to derive them for you, so I hope you've seen them before. And then we write this as x given y is normal mu x given y, sigma x given y. And note the nice property here that the conditional variance of x given y equals little y doesn't depend on the value of y. In general, for a conditional distribution, both the mean and variance depend on the value you're conditioning, but not in this case. This formula kf1, kf2 seems to need sigma y to be invertible. If it's not invertible, you can interpret sigma y inverse as a generalized inverse and the equations still work out. So to write down these Kalman filter recursions, we're going to define some notation for the quantities of interest. We know these filter and prediction and smoothing distributions are going to be multivariate normal. So let's define notation to talk about their means and variances, which we'll call the prediction mean, prediction variance, filter mean, filter variance, smooth mean, smooth variance, and so on. And these are the things we want to find out, right? And really KF3, KF4, KF5 are just definitions setting up notation for what we want to find. Here are the famous Kalman matrix recursions, which can be derived by applying the properties of linear combinations of normal random variables to using the general POMP recursions. We get KF6, KF7, KF8, and I guess this bottom one is KF9. These, first time you see them, particularly KF9 looks like a fairly horrible expression. So, well, let's think about how these are derived. Here's something of an outline derivation. And actually the first two recursions, KF6, KF7, are not too bad to work out if you know the property that is X is a d-dimensional multivariate normal, then AX plus B is normal A mu plus B, A sigma A transpose. And the prediction step is really exactly of this form, taking a linear combination, adding in some noise, and just doing the mean and variance calculations accordingly. And then you get the mean and variance depending on the previous filter distribution. And to use what you know about the normal distribution in this situation, you need to use the fact that multivariate normal identities such as KF1, KF2 also hold when all variables are conditioned on some additional joint Gaussian random variables. In this case, y1 to n minus 1. Once you condition both sides on that, it looks simpler than, well, it works out simpler than it initially looks. For KF8 and KF9, there's a trick to work them out. You can write out the joint density fx and yn given y1 through n minus 1, and then because it's a joint Gaussian density, it'll have an exponent. You can complete the square in terms of x, and then you'll if you're trying to find the conditional distribution of x given y, you can take the joint density, and then everything that only depends on y essentially can only show up in the normalizing constant. And then you don't have to calculate the normalizing constant exactly, because you can work it out later once you've worked out the part that depends on x. Then the other part just must be the right normalizing constant for the multivariate normal density. Working the derivation of the Kalman recursions not central to this course, so I'm not going to go through all the details, but working through the algebra, at least to your own satisfaction, is a good exercise, getting your hands dirty with that. So the thing we most need to notice is that the Kalman filter matrix equations are easy to code, right? They're a bit messy, but you write them up and it's 4 lines of code if you're using a coding language that allows you to write matrices. They're quick to compute unless the dimension of the latent space is large, and so you're in a good situation. If with care in really large models such as numerical weather forecasting, you can even scale up these calculations to massive dimensions such as 10 to the 7. And there's similar calculations giving the backward Kalman recursions, and if you put the forwards and backwards Kalman recursions together, you get Kalman smoothing, though we're most focused on likelihood evaluations, so really Kalman filtering and prediction are the things we most need.